the risk of so this is the third session of the webinar optimization of crop irrigation under the risk of salinization using agrohydrological tools, mainly supported and taught by Dr. Meysam Rezaei. Dear colleagues all over the world, greetings from Valencia and welcome to the webinar. And at the end of the webinar, I will make the announcement of two other webinars dealing as well with modeling. And by now, it is time of Dr. Meysam Rezaei that he will take the floor, assisted with Maria Koniuskova, and for presenting the study cases and other issues related to the webinar. So Dr. Meysam Rezaei, the floor is yours.
Thank you so much, Professor Jorge. And good morning, good evening, good afternoon to the participants. You are most welcome to our webinar, the session 3. During the last 2 weeks, I got feedbacks from Germany, from Argentina, from Spain, from Portugal, Nigeria. Regarding to the modeling, they have some problems or questions related to groundwater level and the boundary condition, and also the EC of irrigation, water of irrigation, and also the groundwater. So today I wanted to show you how we can use those data into the model, and based on the data set that I have, based on the publications, I shared with you the link. So I will go to the publication to explain a little bit, and so do you have this publication on the screen?
Yes.
Okay. So in this work, we have the situation like groundwater table with different salinity during growing seasons, and also the irrigation water with different EC. So we wanted to model it, the groundwater fluctuations, the electrical conductivity of soil layers, and also groundwater, to see what will happen, and also some management regarding to irrigation and also fertilizer application. I don't want to go to the detail of the publication, but I will show you the figure 4 for one profile. Yeah. Just a moment. This is the figure of the one of our field. We have the rotation of cotton, wheat, and maize, and different values. We measure the volumetric water content of different layers, and also the groundwater level and EC of groundwater level, as well as we had the evapotranspiration and also precipitation. So I will go to the model, briefly explain what we did, and then we can come to this graph, or also we can have this graph on the model itself. So we'll go to the model. Do you see the model?
Yes.
Okay, cool. So in the main process, we wanted to inversely calibrate the model based on the water content of the soil that we measured, and also the electrical conductivity of layers with different observation point. We wanted to simulate water flow, solute transport, but here we did the standard solute transport because we didn't have the composition of the whole composition of the soil solution during the season, but we measured also only EC. We also take into account root water uptake, and because here more like advanced modeling, because we use the inverse solution, and in inverse solution we try to estimate soil hydraulic parameter as well as solute transport parameter, and we had the resident concentration, the liquid phase of our in our case. And we had like 128 points of observation that we put them here. And we had two soil materials with depth of 2 meters. Why we choose 2 meters? Because the groundwater level fluctuated within these 2 meters. So we had to take into account all the fluctuations. So we decided to have the profile of 2 meters. The unit length, the length of is in centimeter. So we have like for 3 years, 532 3 seasons, let's say. And we had we recorded 532 of boundary conditions like evapotranspiration and precipitation. So we use those values in the model. And for printing time, we put every 2 weeks, generate the result. We didn't change the iteration criteria here. So we use the Wangen-Ochtana Muallim as a hydraulic model with no hysteresis and dual porosity. And here you can see we have a different, all the materials are not in the window, just one by one, because we have to check which parameter should be optimized based on the observation of variables. So we have the initial value of hydraulic parameters of first layer. We just check these parameters that we wanted to optimize. This is for first layer, and this window is for the second layer. I'm not talking about the values, but the procedure. So we said next. Here, as a boundary condition, we have atmospheric boundary condition with surface layer. And for lower boundary condition, we have variable pressure head, which means the fluctuation of groundwater level. So as an input, we have leaf area index and potential evapotranspiration, and we use the extension coefficient based on the literature and different kind of crops. So since we have a inverse solution, we have iteration criteria for the because we want to optimize the dispersion coefficient of solutes. So we have to use or change the iteration criteria. For the mass unit, we said, okay, milligram, the unit is in milligram, and pulse duration is like whole season. We consider it for whole season with one solute from top of the soil as a irrigation, and also we have the concentration of groundwater, which I show in the variable boundary condition. So this is the solute transport reaction parameter for first, or we have one solute as a EC, and the dispersion, as I told you, we can take it from 1/10 to like 1/20 of the soil depth. as an initial values, and we checked it as a to be optimized. So for RO is the bug density for first layer, and also we have the these values for the second layer, and also we checked it for the dispersion coefficient should be optimized. So as for the boundary condition, upper boundary condition is the concentration of like irrigation, and lower boundary condition is also the concentration of lower boundary condition. And initial condition is the in the liquid phases, as a like we measured in the laboratory, the saturated paste of EC of soil. So we used again the FEDES model for root water uptake, and we just check one for critical stress index is the example. So we use the database is with, we can change it, but based on the literature, we didn't see too much differences between our crops. However, we played with that at that moment. And this is the threshold that we selected from the data set, and potato was the something between the cotton, wheat of our rotation crops. So here the value of boundary conditions, we have the time as started from 1 to 532. We have precipitation and irrigation. We have reference or potential evapotranspiration, and also leaf area index we measured in the lab, in the field, and also groundwater level that we collected from divers or measuring from top of the soil. One thing I should note here is that the groundwater level should be in minus, because the reference of our system is top of the soil, and start from the top of the soil to the end of the profile, it should be in minus values. And C top and C bottom is the EC values of irrigation, and C bottom is the EC values of groundwater level. It is corresponding to the groundwater level, C bottom, and C top is corresponding to the irrigation water. And you can see sometimes it's constant and sometimes it different because of the measurements. And yeah, and this is the values that we have in our hand. We put all of them into the model. So here is the new window that I want to show you. As I said, we had two kind of measurements during the growing seasons. One is the EC of each layer or each points, observation points, and also water content. We put the EC values as a Y, and X is a time. You see, the time, the initial time is 1, and in different times, we measure the EC values of each point. The type number 4 related to the concentration, actually the EC here. And number 2, in some cases here, we have the water content. Before explaining the position and way, I will go to the help window. And in help window, you can find out the different types. For example, in our case, number 2 is water content, and number 4 is concentration or temperature, if we want to evaluate the temperature and other things. So based on the object or target, we will check the type and also the like X. You can find out everything from the help menu in the window of the model. So the position here is the observation point, which means we have 1, 2, 3, 4 at different depth of the soil. We measure like water content here. You see the values is like 0.27 almost near to the like field capacity. And the EC values in deciments per meter. So this is the input values for inverse solution, which means the observation of the model. What does it mean in inverse solution? It means based on the observation that we got, we will try to optimize or find out the hydraulic parameters of the soil layers and also the coefficient of each solute, the dispersion coefficient of each solute. And based on that, we will optimize it, or in other way, we calibrate the model. And then after that, we can run the scenarios, different irrigation schemes, different like concentration we add as a fertilizer with irrigation to see what will happen in the system. So this is the window of our profile, but I will go to the graphical editor to show you the material. You see here, we have two materials from 0 to 60 and from 60 to 200. And the root water uptake, as I explained previously, it's like the density is like in 25 centimeter. And the observation point, as you can see, we have in at 10 centimeter, 28 or 30 centimeter almost, 45 centimeter, and 100. So this is the model and all the information that we put into the model. And once we run the model, it takes like half an hour or even more or even less to calculate the parameter of the soil, hydraulic parameter of the soil, as well as the dispersion coefficient. So once it finished, we put enter, hint enter to have the result here in the right side of the window as a post processing. So I want to go to the inverse solution to show you what the model generated here. As you can see, this is started from, we have some information, the initial condition, initial values of hydraulic parameter of the soil from first layer, second layer, and also the solute transport parameter of each layer. You can see this is the information that we input into the model. And this is the parameter estimation starting from the initial values. And we have the correlation matrix between the parameter to show, in this case, we have to look at the correlation matrix. If parameters are correlated together, we have to reduce it, or we have to do the sensitivity analysis to reduce the number of parameters to be optimized. But here in our case, we didn't have any correlation, any significant correlation. So this is the result of the model, the optimized values for example, water, saturated water content, alpha N, and hydraulic conductivity, saturated hydraulic conductivity of first layer, and also the second layer. So with the dispersion coefficient of the second. So you can see the model gave us the statistical evaluation of the result based on the observation, I mean the water content and electrical conductivity. And you can do this evaluation separately in Excel file or using the coding with R or Python to read the data from the data file and try find out the different kind of statistical. So this is the file of the inverse solution, which means now we have the data set, and if we want to evaluate or do the scenario analysis, we have to use these values as a hydraulic parameters and run the model in forward mode and do the scenarios. Okay. Let's go to the observation point, to the result that generated by the model. Since we have the water content, if we go to the observation, you see the points are the observation that we put into the model, and the lines are the simulation. And we can see based on the optimized value, we have the less mismatch between the observed and simulated values. Of course, you can add the legend here by clicking on the edit chart data to see which color or which line correspond to the which that actually depth or observation point. So we can go to the, for example, concentration. And this is the concentration, the EC values in the model. And you can see there are more close to the observation points. So we are very satisfied with this results. To be honest, I run the model like for like 100 times to get this kind of result, because I played with initial values, I played with adjustable parameter to see which one is suitable for the for in our case. So I would suggest you, if you want to run the model with one run or with one execution of the model, you cannot get any reliable result. You have to play with that to get the most reliable results. So this is the, for example, observation point for concentration and also water content. If we go to, for example, here as a boundary fluxes, and we evaluate the bottom fluxes, for example, to see what is the difference or fluctuation of groundwater level. You see the fluxes at the bottom of the profile is like this. We have like input or income inflow from the bottom of the soil, and also outflow during the drying season. So and also we can show you like pressure head. I wanted to yeah, okay. We have the cumulative infiltration, and you can see how much water infiltrated throughout the soil profile. And of course, you have all this data in the text file in the directory of the project, and you can use those files as well as the these graphs here. And let me find out the bottom pressure head. And you can see here is the fluctuation of groundwater level during the growing season that we simulated. Everything, and you can consider like if you have a snow, if you have like you want to evaluate the infiltration, the leaching, you can have a look to this option, water flow boundary fluxes and head, and you will see the results of simulations. So that's it from the model. Most people ask me how we can input the data set as a groundwater level to the model. You have to define in minus values from the surface, and check the boundary conditions to have to define the most appropriate boundary condition, upper boundary condition and bottom boundary condition, and run the model. So I was very satisfied with this paper, and we evaluated with different kind of scenarios and also different fields with cotton, wheat, maize rotation, and also rice and wheat rotation, and we evaluated it. And the model was very successful in the rotation of cotton, wheat, maize, comparing to rice, wheat, as you can see in fig 3 of this paper. You can go to and read this paper and just have get the idea what we have done based on the explanation that I gave you on the model. So that's it from my side based on the questions, and I'm ready to answer your question in your cases. So Maria, the floor is yours, and the floor is, and the participant can ask their question.
Yeah, thank you, Mason. So as I wrote in the chat,
Yeah,
everyone who would like to run their model and to
yeah.
share it with us, so they are welcome to raise their hands, and I will move them to the
So
panel.
okay, so I am stopping the share screen. Okay. Mm.
Dear participants, please raise your hand if you want to run your model and to share with us the problems that you have.
Yeah, if you run the
running.
model, if you have any question, you can ask. Yeah. Uh, uh, just explain that I had I'm in contact with the Andres from Argentina, who had the similar data set as I showed in similar to our case, and we can set up as the model that I showed you and run the model, but the data set is related to his PhD, so I would not show the results, the data set here, and maybe after get published, so he can explain us maybe later on in different webinar, different conferences, how he will do. So yeah, this is a nice question. Yes. Maybe Maria, people ask the question in the chat. Can you?
So I noticed that the units for solid were mass solid, volume of water, but I believe that electrical conductivity of X-based texture can be used instead.
Yes, we can convert the mass to the different unit using the bulk density of the soil. If we multiply it by the bulk density or divide it by bulk density, we will have the mass, and then we use into the model. And actually, the model gives us the EC of the soil solution, not saturated paste. And it's a little bit like uncertainty of the data set, but we have with the data, and we run the model, and we get the best the options based on the unit that we select.
And also, participants asked to share the DOI of the paper.
I did it, and I do it now. Yes. Here you go. You can download it and read it. And I have seen Mustafa Abdullahpur raise his hand. No?
See, I don't see any raised hands. Or maybe I should. So Mason, if you see the raised hand, could you please move them to the panel because I don't see.
No, I don't see.
Now I see. Okay.
Yeah. We can.
Mustafa, please accept the invitation. So meanwhile, Mason, we have a question in the Q&A about other models, so especially the ones which can help to model the soil water in the profile.
Different models. Yeah, we can change. If you mean the hydraulic model, yes, we can change to the another one to see what will happen to the model and the results. And for the, I see that actually in the model we have to have the Gaussian coefficient, and I didn't use the another coefficient. I have to look in the user manual that if it's possible or not. Actually, I don't know by heart to say this.
So I suppose the question is related to other models, other than hydros.
Actually, it is more sophisticated, but yes, we have like SATMOD, which can help us to simulate like salinity in the soil, and also SWAP, I guess, can help us. But yeah, the hydros itself is very sophisticated and yeah, so modern. And the new, like the update model, and then you can use. There are several models actually. As I shared the website in the first session, you can find out which kind of model you want to use, and of course depend on the available data that you have. Based on the data, you will use different model.
So Mustafa, you're welcome to raise your question. We cannot hear you, Mustafa.
Do you have my sound? Excuse me.
Yes, now we have.
Thanks, Mesa. I asked my question in the chat, but here I also would like to talk about it more. It is related to the ion exchange reaction in the soil, and in the model, the Gaussian coefficient was used. But my question is, can I change the model, change the ion exchange coefficient from the Gaussian coefficient to the gain and Thomas?
Yeah, I explained, I saw this question, and it's a really nice question. I didn't actually go to the different like model. I have to look at the user manual to see is it possible or not. I cannot say by heart now. We just have a look to the manual to see if it's possible or not. But mostly we have to use the Gaussian coefficient.
Okay, thanks.
And it's a like calculation between the ratio of different cation, you know.
Mm-hmm.
Yeah.
Okay. Also, I have another question. Can I can I ask or? Yeah. Okay.
Yes.
For the column experiment, when I asked you before,
Yeah.
contact, yeah. If the direction of the irrigation will be from bottom of the column,
Yes.
what we should do or how we can introduce this into the hydros model?
Actually, if it would be like a constant head, you can use the boundary condition as a constant head. If it would be variable, then you have to measure the depth of or pressure head from the bottom of the soil. If you have, because the reference is top of the soil, and just record the depth of the water from the bottom, and you will have the data set. And also you have to record the EC values of that water. So based on reduction of the depth of the water level, you will have the different or fluctuation of groundwater, let's say, in your case. So you will have the different or variable pressure head from the bottom. You could choose constant or variable. Yeah, as I explained, you already asked me, and yesterday or 2 days ago, I didn't find out the time to have a look in detail, but we can solve it in our like short meeting. Just have a look to the model and then try to find out the solution. But yeah, that's the way that we can do.
We will manage a meeting and then we can discuss more about it.
Yes, yes.
Thanks a lot. Thanks for thanks.
Thank you so much. Yeah, actually, Dr. Hashiminejad is helping me to explain about different models, as I said, like SATMET, like aquacrop. But actually, aquacrop is a little bit weak in salinity, but in as a crop modeling is very well. And yeah, from the Jorge, yeah. So yeah, you can use those model as
So Mason, if we go to the Q&A box, the next question is related to the groundwater table. So we input a groundwater table data, and output results also showed bottom boundary values.
Yes.
Are they both the same?
Yes, actually the variable boundary condition is the same for both model. But we just changed the model because we have different kind of hydraulic parameters for corresponding to each model. Just it. But for the rest, for the other parameter, other variable and input, they are the same. So no worries about that. And we had another investigation regarding to the model, the hydraulic models. And in some cases, Van Genochten and Muallem have worked very well, and in other cases, Brooks and Corney. So you have to evaluate which one is the working well with your data set as well, yeah, in calibration process.
May I? Yes, this is just to comment that there exist several models. And the reason is that every model has its own speciality. And some of the models perform better tasks than others. If you are interested, for example, in crop development, it is not the same as if you are interested in reactive transport into soils and mineralogy and things like that. And as well, our idea is to prepare a series of webinars that can give you the option to approach to the modeling. Dr. Hashemi mentioned wetsuit. Wetsuit is let's say it is rather than a model is like a calculator that you put some inputs and it gives you steady state condition and some forecast, and it is very easy to use, but of course has not the power as other model so complicated as this one, as Hydros, that has so many possibilities. And as well, because of the extent of the webinar, it is not possible to explore all possibilities, of, for example, of Hydros. But Hydros can deal with heavy metals, pesticides, and many other things, because can link to other well-known models like this of the geochemistry. Yes, frequency and other models that are, yeah. And I think that modeling is a very difficult task. Any model will give you an answer, even if you are not experienced. The point is that you start, those that trying to start with modeling, start with easy cases and make more and more complex progressively. So the first task that you must ensure is that water movements or hydrological aspects are close to reality, because if not, other things will fail. I mean, chemistry will fail because it is associated to water. And so I think that the best is first fitting the hydrological part. And when this works, then you add some other complications dealing with chemistry and so on. So modeling is complex, and any model will give you an answer. But this could be without meaning. I mean that do not match reality and can make you to take wrong decision. So I announce you now that you will receive in your email in due time an invitation for next week for the SaltMed model. That is another model with another approach. For example, is stronger in the way of irrigation. It is easily adapted to drip and sprinkler and furrow, and has some advantages and some disadvantages. Aqua crop is more will follow in the next week the webinar, and this model is dealing mainly with crops, and it is important to have an estimation of that and minimize the aspects of the reactive soil transport. But it can be useful and maybe easy for you. And there are other models as SWAP. And so our idea is to give you a panoramic on the models, and maybe you can make later a discussion about what model did you find more useful for your study cases. And this is my general remark. And by now, I want to make a question to Dr. Mason Resey, because it is very important, and it is usually misunderstood by modelers, is that the predictions that, well, if I want to make that as a question, I must do in another way. So you get estimations of electrical conductivity.
Yes.
But how it is the relation with the soil saturated past extract conductivity? This is the point, because many people do not relate that accurately.
Yeah, actually, we have to have the like a equation with the converting the EC values of the soil solution to the saturated paste. So that's one thing, and another thing, the model generates soil water content as well as the EC. We can correlate the EC values of simulated actually and water content to see these values correspond to this amount of water that is or soil contains this amount of water. And that's why I said this is the EC of soil solution, not the saturated paste. And if we have the conversion coefficient, we can convert the EC of the model to the saturated paste. Yeah, and also if we have the saturation condition, we have to find out the equation from the observation as well as the simulation. We can compare these two equations. Several publications also deal with this. They try to measure water content and EC of soil in the field. They correlated to each other to find out the equation and run the model, and also they have different equation and compare the equation with the simulated values and also the observed values. So more or less close together once it's optimized or calibrated.
Thank you, Mason. So the next question that we have in Q&A, I have experimental results from a lysimeter with 3 plants.
Yes.
The lysimeter measures 110 centimeters by 110 centimeters to 50 centimeter depth.
Yeah.
I'm trying to model one plant as a 2-dimensional axis symmetrical.
Yes.
The lysimeter bottom has a seepage face with 2 extended rock wool pipes of diameter 5 centimeter and 45 centimeter depth below the lysimeter floor. How do I simulate the bottom surface for one plant?
Actually, if you want to go to the 2-dimensional simulation, you have to change the model to 2D, and you need to have the license, buy the license and run the model. And this exactly the conceptualization of the model. You can put all of the information in 2D at the bottom, at the top. The boundary conditions you can define in different way, completely different. I mean the conceptual of the model, the boundary of the profile into the in 2D model. But in 1D, it's a little bit tricky to have this kind of boundaries. However, you can simplify it, the situation, and try the 1D. And more or less, you can get the result similar to 2D. However, it's a little bit has a little bit uncertainty.
A comment.
Yeah.
To the chat window, to Dr. Hasmenijad and Dr. Anna Paz. Remember that the dilution in salt-affected soils can affect the composition of the soil solution. It means that it is not just a matter of diluting or concentrating the value you have. If you want to approach a, how to say, more physicochemically sound model for making in your experiments, making an approach to what is the actual electrical conductivity of the saturated past or on inverse of the soil solution and the soil moisture you have. You can download that from the Salinity Lab. There is a model that can deal that as well, taking into account the clay mineralogy and clay content, and as well the solubility of the salts that you have there. So the more accurate, the idea is that the more accurate you want the results, it is more complex or more input data you will need. And so it's a good idea to start this easily and getting skilled and to face more complex problems. Thank you.
Thank you, Jorge. So, Mason, we can move with other questions.
Yes,
so did the presence of organic matter have a significant effect on the results?
Yes. Actually, we have one scenario in that paper that we have the different component of organic like fertilizer or let's say manual. And we changed it changed the hydraulic parameters and also the EC values and other things. Indeed, using any chemical fertilizer or manual or organic fertilizer or organic matter can affect the results, and you can specify, because once you put some organic matter into the soil, the bug density will change and the composition will change, and then you will have different initial condition, and so you will have different result as well. So yeah, it's affect. And you can do for example, scenario analysis to see what will happen in soil water content.
Okay, so the next question is, which model parameters are most affected by crop type or agricultural practices?
Actually, it's really tricky question, Sometimes once you have to do the sensitivity analysis to see which parameter are more sensitive. Mostly saturated hydraulic conductivity, or I don't know, alpha and N are sensitive as a Van Genochten-Moellem parameters to the actually we would say the results, the water content simulation is sensitive to those parameters, so they all should be optimized. And in different articles or different research, we will have different results. For example, in my case, in my PhD, saturated hydraulic conductivity, alpha and N were the most sensitive parameter, but in Wohling, in 2012, they did a research and they found out the theta R and theta S and also K-SAT, saturated hydraulic conductivity, are more sensitive. So they try to optimize those parameters. That's depend on the situation of the profile, the initial condition, and also the hydraulic parameters of the model, and also the most important thing is that the observation. And as you remember, in first session, once I explained, and also Jorge explained in the beginning, we have to look for uncertainty of observation as well before going to the modeling approach. So that's the first step. The next step, doing some sensitivity analysis or uncertainty analysis on the modeling itself, and try to calibrate the model and validate it. And then, you will have some other scenario analysis, because the approach is that we try to calibrate, validate it for scenarios to see, okay, if we change something or if we decide to different management, what will happen to the system. And of course, we have some uncertainty on the result, but it gives the trend. Yeah.
I think there are still some lost questions. For example, does organic matter affect the results of the model? And I think that you can go to the Rosetta part and show that if you have this organic matter, you can make this as neural network prediction.
You mean I should share the screen to just show you how it change? Yeah. I'll just make a new one, like a test. So it's just an example, just put the water flow, and for geometry, one material, and 10. It's just an example, you know, we just want to see. Okay, here, this is the parameter. We have the loam soil, and this is the value of the hydraulic parameter. Saturated hydraulic parameter is like 25. Let's go to the neural network, say Rosetta. And if we add the organic matter.
And bulk density as well.
Yes. For example, we have sand, silt, clay, and we will put it here like 20% of sand, 35% of silt, and like 45% of like clay. Just an example. The bulk density would be like 1.4. The field capacity, like, I don't know, it's just an example. 24%, and for wilting point would be like 5%. Okay, we predict it, and you can see the saturated hydraulic is 22. Yes, theta R is like 0.3. Theta is like 30%, 40%, alpha, and etc. So if we add organic matter, and the bulk density would be like 1.3, the theta, the field capacity would be like 26, more or less, and wilting point would be like 8. And if we predict it, you can see the hydraulic parameter changed, and saturated hydraulic conductivity, estimated at 27. 5 more than the previous one. And you can see if we add some organic matter, we change the bulk density, like water content at field capacity or wilting point will be changed. So we have different values of the hydraulic parameters. And within this, we will have different results. Was it clear?
I think so.
Yeah. So again,
another remark is that this model can run at a high ionic strength in the soil solution. And this makes difference with other models that use the vehicle or Davis approach to the activity coefficients. And so this database is special, dealing with high ionic strength of the solution that makes a challenge to compute. Yeah.
Yes, and normally I would note that the Rosetta is the black box, and based on the data set from US, and sometimes it's different from the soil from, for example, in my country or different countries, because it's like a pedo transfer function somehow. So the pedo transfer function with different soil is different. So maybe it's not correspond to the values that you in reality you have in your field. This is just the initial estimation. Because of that, we measure the values in the laboratory and put the measured value as the initial value instead of using the Rosetta. But it gives us the like initial values to start the model.
Answering to Elbaiden et Saura, your idea is interesting, and we developed that approach in a devoted webinar that is recorded and is available, that it is eAlof, with different persons presenting the cash value as cash crop of the alophytes, and as well the nutritive compounds that can be extracted from halophytes especially, and as well medicaments and so on. So I recommend you to come back to the review of this webinar that is called e-alof in our series of webinars.
Yeah, thank you.
Thank you. So then do these models work good for high residual sodium carbonate waters having high pH?
Yes, actually. If we put, as you remember, for example, major anion chemistry module or INSAS, which is implemented into the model, we can define the composition of alkalinity or other composition of the water. So based on the values that we put into the model generate or calculate the pH and also simulate the pH.
Yes, there is some aspect that is important, actually most of the data that appear for carbonates and bicarbonates are attributed to that this is carbonates and bicarbonates. But in the labs, what usually is measured is alkalinity. I mean, all components that react with acidic solution. And well, this can be discriminated, but if other components like silica or nitrates or ammonium that usually are not determined are there in the solution, well, the estimation of the carbonates and bicarbonates can be altered. But well, it is well known, and as always, the models give you an approach, and you must have a clear idea and a conceptual model for what do you need the model, and maybe an approximate answer is better than you are looking for a very detailed one that could be erroneous.
Yeah, thank you.
So the next question, I'm not sure that may be clear, but maybe you understand. Then how exact data can be generated for soil salinity problem of any area? So
Pardon? Which?
Maybe we shall ask to specify the question.
Yeah, actually, you know, sometimes
maybe that the exact data cannot be generated. I don't understand.
Actually, we have to go to the field, collect some soil and measure in the laboratory, or we have some portable devices and measure in the field. And also we can use some integrate like using like EMI technique to measure the EC in the field, convert it somehow to the ECA to ECE or soil solution EC and put into the model. It's impossible, but of course we have some uncertainty based on, and we can discuss based on that uncertainty what will happen. And we can run the model for different location and based on the time interval that they use with different devices.
Yes, this point I tried to stress as well during my presentation first day, that you can take measurement at certain times, but this could be very useful or needed for calibrating the model and later for validating the results. But with a model, you can make a forecast of what will be the conditions. Probably they are not exact, but you can run different scenarios. Imagine the more clear example is with climate. You can take an average year of rainfall, but maybe the year that you will try to forecast will not match this hydrogram. This iodogram. So it could be drier or could be wetter or could be in different times the rainfall. So the results they will be different in reality. But with model you can make so many scenarios as you want, and then this will give you an idea of how the system works.
Yeah, and you can see the trend of the risk of like salinization, you know, in the future. You see. Yeah.
So there is a question following up the question about organic matter. So there is no option to include organic matter in the software independently?
I didn't see actually. If you want to look at the like particle movement, there is an option in the model to look for that, or that it's the idea is the like movement of the nanoparticles into the model. But yeah, for the matter, like organic matter, yeah, I didn't see any.
It is just indirectly reflected as the cation exchange capacity and as well in the coefficients of absorption. I mean the Scapon coefficients, but not directly as far as we know in this version of the model. But if you link to the happy one, there are other sub models that can deal with that. Because there's frequency model that can be linked. This can deal with organic matter and specifically absorption and well, it is other complexity.
Actually, the frequency model is implemented in the hydros, and you have to know or you have to have some knowledge about the programming, because once you just select the HP1, which implement the hydros and frequency, you have to program that chemical component and then some equations to run the model. It's a little bit different or tricky from the hydros itself.
Yes, and for those that in your laboratories are you measuring the soil saturated past and you want to change to estimate the composition in other soil moistures, you can, in the chat window I will send you the link to the Salinity Lab model that is called Extract Chem that ask you for soil mineralogy and well, several aspects, and the concentration in moles of some solids that can be dissolved or exchanged, and in this way you will get a better approach than this rules of thumb that converting 1.5 to soil saturated paste and so on.
So at the moment, we addressed all the questions from the Q&A box. So we can, if there is no more questions from the audience,
so
we can wrap up.
May I add one sentence and then you can wrap up? Dear participants, thank you so much to being here with us. And we did a lot of efforts, a lot of times to prepare this kind of webinars. Maria, Jorge, Kate, as a steering committee of INSAS, I would like to thank them, and also FAO, which gives us this kind of floor to talk to you. And I'm available if you have any question regarding to the model. If you have some data set you can't, or you need some help, I'm ready to help you to run the model or get any publications. And also you can find out some information in PC Progress website, which is specified for hydros by the author of hydros.
There is a question. There is a question of Omram Al-Sihabi, and yes, this is the easiest way to use the hydros, because it is first task I recommended, that is adjusting the hydrological part of the model, and then without crop, and maybe with only one event of irrigation or something like that, and then you change the limit properties, and then you learn about the model, and then when you dominate that, you can add more complexity. And from my side as well, to thank especially to Dr. Maison-Rasey, because he has done a big effort in preparing the materials, and I'm sure that he has explained that in a way that makes people easy to start with the modeling. And I'm sure as well that he will be willing to help you if you start this way to solve difficulties that are always found in the running of the models and so on. And so before closing the session, I again announce, because it is very close, the next webinar, and the flyer will be ready, I think, on Thursday. It will be on your email. But I want to announce that next week, as well on Tuesday, same time as today, we will have the presentation of the SALT-MED model. And the next week, we will have as well on Tuesday and same time the presentation of the aquacrop model. So you are invited to come with us through this travel of different models, because different interests could make interesting using one model or another one, or combining them. So thank you very much to all you attendants. Thank you, Maria, Dr. Maria Koniuskova, for your assistance. And again, Dr. Maison-Rasey, for your excellent presentation. And thank you all, dear colleagues, for attending the webinar. And we keep in touch. So have a nice weekend, and we meet next week.
Thanks to all, and goodbye.
Bye-bye.
See you on the next webinar.
Yeah. Thank you.